Greetings everyone. Today we are going to discuss Pythagorean tuning. What are the main problems of Pythagorean tuning and how we can solve these problems. First, let's summarize what Pythagorean tuning is. Pythagorean tuning is a tuning system that is based on perfect fourths and perfect fifths. What is a fourth and what is a fifth? A fourth is basically the distance from C to F, and the fifth will be the distance from C to G. The fourth will have a mathematical ratio of 4/3 when it comes to frequencies. For example, we have like 128 Hertz for C in this place. If you have 4/3, it will be 170.666 Hertz. So the ratio between these two frequencies will be 4/3. If we have 3/2, we will get 192 Hertz between C and G. So this is the perfect fifth. The perfect fourth and the perfect fifth are interrelated because if you have 2/3, it's basically a fourth lower than is the reversal of fourth, in fact, an octave lower than the other F. We can see it in the Hertz, 85.33 multiplied by 2. This is what it gives us. So now that we addressed what Pythagorean tuning is, we are going to start to build our scale. We are going to build multiple perfect fifths: C, G, D, A, E, B, F sharp, C sharp, G sharp, D sharp, A sharp, F, some sort of F, and now we are reaching some sort of C. But this C, it's not the same C as this one because it's one Pythagorean comma higher. Now we are 7 octaves above, but we are just one Pythagorean comma distance when it comes to like the absolute notes. If we normalize everything, we are going to see the Pythagorean comma here. It's a dissonant interval. And now we can also show it in some other way. We have our F here, some sort of F, that's a Pythagorean augmented third, but not a perfect fourth. We are going to see this comparison by having the absolute pitch of 2/3, and they will be one Pythagorean comma away. When we are going to normalize this one, we are going to have the perfect fourth and the augmented third, which is one Pythagorean comma higher. Let's click OK, and now we have our tuning system. Let's put only one octave now. For now, we have C, F, C, but we have the Pythagorean comma here. This gives us the wolf fifth. It's an imperfect fifth, which is not as harmonious as this fifth. So what can we do to solve this problem? This will be discussed very soon, but first and foremost, let us discuss the other problem of Pythagorean tuning that people complain about. One of the main other problems that people complain about is the fact that the E is quite sharp in comparison to the C. So we have a very sharp major third compared to just intonation. This is called a Pythagorean major third, and we'll do a comparison with normalize. Okay. Here we have the just major third and the just major chord. And now we have the Pythagorean major third, which is a little bit more dissonant, and the Pythagorean major chord. And these are the two main problems of Pythagorean tuning. My solution to solving these problems will be to just use the Pythagorean comma not as a burden but as an asset, because we can use it in a microtonal way to get some extra notes. We have our 3/2 here. We can just go up to the 53rd octave, and up to the 53rd fifth, not octave, and we get some sort of other C, which is very close to the 31st octave. So the ratio is almost 1, so they are almost equal basically. The distance in cents will be around 3.6 cents, I think. Yep. So it's a very, very small difference. This comma is also called Mercator comma. A very small comma that we get here, where the octave will be basically sharpened. Let us normalize, and here we get Mercator's comma. If we just basically add 1 to 0 3, we can just now remove the octaves and sort everything in ascending order. So basically this is what we will get: a tuning based on Pythagorean commas. Everything will be almost just, apart from the octave. And we have basically two types of comma: the big Pythagorean comma and the small Pythagorean comma. The big one is the 12 comma, and the other one is the 19 comma, if I remember well. And this repetition gives us basically our tuning. So what we can do to just solve the problem of the octave is to shift the problem somewhere further. Instead of having basically a series of 53 fifths up, where we do not get our perfect fourth at the F, we can just basically go 26 fifths up and 26 fifths down, and then get the octave. Let me show you. We'll just go like this, and with 26 fifths up. Oh, sorry. and then we'll go 26/5 down. Till we get to 52. So basically we have some sort of B flat here, but it's not really like the B flat we use usually. It will be one of the dissonant tones when compared to this kind of E flat. They will be at basically at the Mercator's fifth, which is around basically like 699 cents or something like that. It will be flat fifth here, but it's pretty much the same size as the tempered 12 tone equal tempered fifth, so it's not like something that dissonant, especially if people are already used to the piano tuning. And now we get a lot more consonant tones compared to what we had previously, since we get all these names in Scala. Okay, and now we have perfect fifth all over the place, and no whole fifth will be necessary, because we'll always have a fifth corresponding somewhere in the scale, apart from Mercator's fifth between two of these pitches. I think it will be this one and this one. This will, so number 42, the 42nd comma, and the 16th comma, if I remember well. Two of these ones will be dissonant, but otherwise all of these ones are consonant fifths. Now if you try to add our major third now, it will be very, very close to another one of our intervals, which is the Pythagorean diminished fourth. So basically this one is this. Five over 4. So it's almost equal to 0 here. And now if you get this interval in cents, it's like 2 cents away, less than 2 cents, so it's pretty much unnoticeable, especially when we play very, very fast. So we can just now discard the major third or entirely, because we have another consonant interval here, or almost consonant interval, because the human ear is pretty easy to deceive. I don't think it's that much of a problem now. So now we get perfect fifth here. We have multiple intervals, both the Pythagorean major third and now we get our something very, very close. Oh no, sorry, this is like they didn't shift the notation system here. We have to shift to E53 in order to adjust into, yeah, here. Okay, so we have both our, this is the Pythagorean major third. We have both the Pythagorean major third and something very, very close to the just major third. This was the Pythagorean major third and something very close to the just major third now. Now Pythagorean tuning becomes a lot more flexible, meaning that we can use it for multiple purposes. This is something very close to neutral third. Another interval that we can get. And we can also get our Pythagorean major third. Something very close to the just major third. Something close to some sort of neutral chord now. That'll go a little bit higher. Something basically a little bit more oriental here, because we're using neutral intervals. And here we used something very close to just intonation now. So things become a lot more maneuverable thanks to this tuning. Let us proceed further. Let's say, for example, that we want to explore these commas. Here we have like a sort of a Turkish program, and here I made some accidentals based on Ottoman tuning. So basically we have like the 1 comma sharp and the 1 comma flat. We also have like these system. Yeah, this is the flat symbol that we have in Western music. Is the 5 comma flat in the Turkish system here. But on the other hand, our sharp symbol will be like 4 comma sharp, and we get a lot of different intervals. So I extended this system to include all the commas up to 80 commas now, which is basically like 2 tones up. Now in this system, our scales will be very interesting. We'll get a lot of new scales. So basically we have our major scale. It will have some sort of interesting new derivations. So we have like 53 tone tuning. It will be a 50 tone Pythagorean tuning. Which means that we can get multiple major scales. Now the whole tone will be 9 commas. So we'll get something like basically like the Pythagorean major. 9, 9, 4, 9, 9, 9, 4. we can get something very, very close to a just major. We can call it a just major. 9, 8, 5. 9, 9, 8, 5. We can get some sort of neutral major here. 9, 7, 6. 9, 9, 7, 6. We can get a more lower neutral major, for example. 9, 6, 7. 9, 9, 6, 7. So we get a lot of new options here with this type of tuning. So we can get, for example, our major scale here in C. But we can also get a major scale with just intervals. G. This is the major scale where we basically have the flat A. It's the 9, 8, 5, 9, 8, 9, 5. So it's very similar, but we can get it in just like this and get only like a 2, 1 comma flat notes here. That will be the E and the B. So just now we get 3 different flavorings of the major scale, and there are infinitely many possibilities. Now we can get multiple minor scales too. This will be like some sort of a Pythagorean minor scale, but we can have a just minor scale. And now all types of flavorings can be obtained here. We can also get, for example, a just minor third here. Instead of Pythagorean minor third, we can get it like this. By going 1 comma up. Or otherwise we can just basically discard this minor whole tone and just get the Pythagorean major tone. So things become a lot more interesting. We can get lots of different chords now. We can, for example, get our Pythagorean major chord. Our Pythagorean major chord. We can also get some sort of just major chord. We can get a Pythagorean minor chord. A Pythagorean minor chord here. These small differences can make our music a lot more interactive now. This is why the Turks have multiple microtonal tunings, and that's why also Oriental music is a lot more enjoyable when people listen to actual Oriental music. All these intervals are essential to this music. So for example, we can get some sort of a G just major, which the Turks will call makam rast. Or we can get something closer to what the Turks will call makam ajem here. This would be some sort of B flat major, a Pythagorean B flat major. So it's not a B flat major, maybe rather, let's say, because this one is a G, this one will be F. Yeah, it's a F major. because of all of these different tunings, we get all of the different modes that the Orientals will call maqamat. This will be like rast, this will be ajam. Some interesting ones can be, for example, segah. Yeah, here it will be sharper. Yes, and by playing with all of those commas, a whole new array of music will be shown now. So these commas can be very useful when someone knows how to use them. I hope I solved most of the issues people complain about when it comes to Pythagorean tuning. Indeed, there is the problem that we have to go into microtonality to get Pythagorean tuning to sound a lot more consonant, and to get even further into the commas, up to the point that basically we get 53 pitches per octave instead of 12. But I think in the end it will be like the only solution to get something as consonant as possible. So everybody have a nice day. Thank you very much for watching.